Okay, and we're back. So sorry about that. So let's put rotation aside for the moment. Um, so now we've got the acceleration being added to the velocity, position is being added, the velocity is being added to the position, and let's see what happens. Oops. First of all, let's catch up. Great. Let's see what happens in our game. Oops, and it's gone. And the reason is, this is really, really fast. So let's reduce this down to 0.01. And let's see. Let's just make sure that things kind of make sense. You can see that the ship has been given a speed, and the speed will continue to apply forever. Another thing we can do here is if input get key key code A. Let's play with our rotation now. So transform.rotation is going to be equal to quaternion Euler 0, 0. We need to add our rotation about the axis. There's one way to do this. Goal rotation is going to be 0. Times v direction. Fine. What we're going to do here is, first of all, we're going to create our quaternion, or we're going to add to our angle rotation plus equals 0.1. Let's copy this for D. Great, and we also want to get out of our direction. We want to extract from that our direction, and so let's take our V direction. Well, actually, let's create this quaternion. In fact, I'm going to just make this a little bit simpler. I'm not going to make this public either. Quaternion Q orientation equals to quaternion. And what we're going to do here, this should all be pretty familiar to you at this point. Q quaternion. So this will just a little bit more eloquent, and then V direction is going to be Q quaternion times vector 3, 1, 0, 0. So we don't actually have to do this here. Great. Unless there's let's see, is there a thing? No. Fine. Alright, let's just make sure that our rotations are working. Very, very slowly. Let's also add a quick private float. Angular speed, let's make that 1.0. Right. This should hopefully be a little bit faster. Notice nothing else happens yet, right? I'm just rotating. Let me turn off that acceleration. So now this is just going to be 0. And now what I have is going to be a ship that rotates in space. Now keep in mind, we're not talking about rotation momentum, we're not talking about applying forces in the rotation, but if you were to do this physically accurately, you would do that too. So we're still kind of cheating a little bit, but that's okay. We're not going to talk about rotational momentum in this lecture, or I think in this class. So great, let's go back here. So now let's try to apply a force. And you might already be there. This is actually pretty simple. All we need to do is just apply the force directly, like this. So we can code up a new function, right? Void apply force vector 3 v force. And here we just need to v acceleration, right? If F equals ma, then A equals F divided by mass. Whoops. There you go. And that's it, right? So it's actually that simple. So if, let's say get key code W, I'm going to apply a force in the direction of my in my direction. So my force, v force, is going to be equal to my v direction normalized, right? Time at that, well, now I have to maybe multiply it by some kind of scale factor, which I'm going to just set to float scale factor equals 1.0. What's going on here? Ah, okay. And then apply force, v force. And that's it. And you'll notice that the acceleration will automatically get updated, and down here will get set to 0. This is like our little cleanup area. Oops. All right, let's see what happens now. So now, when I rotate, still works. When I hit W, whoa, gone. Way too fast. So let's scale our factor down to maybe 0.01 and see what's going wrong here. Okay. So now when I rotate and I hit up, it's not really going in the right direction. At least I'm going a bit slower. I don't like the scale factor. In fact, we already have a scale factor in here. The scale factor is in the applied force. So what I can do, what is going on? Oh, okay. Let's get rid of that scale factor and instead rely on our mass. And we're going to set this to, well, it's a ship, right? So it's like 100 kilograms. That seems right. No, it's pretty slow, but whatever. Actually, this is going to give us the same effect as scaling it down by 100 to 0.001. So it's not bad. And so let's set it to 100 kilograms with a force of 1. Great, I love how my head is very, this is very accurately tracking my position. I'm going to turn this off because it's becoming a bit annoying. There we go. Great. A little bit better. Now you can see my background as well. Cool. Let me make me smaller. Woo! All right, so now we got that. But you'll notice that the acceleration is not being applied in the correct direction. Why would that be? Well, you'll notice that this direction here is being applied before the angular orientation is being set correctly. So let's first of all fix that. Okay. Oops, I keep on hitting F5. All right, let's see. So now if I want to go to the left. Oh, still going the wrong way and still going way too fast. So let's still slow it down by the mass, even more. All right, well, let's see. When I rotate to the left like that, I seem to go up. If I don't rotate and I go up, I'm going the wrong direction still. Okay. So, oh, sorry, my acceleration should be plus equal to the v force divided by the mass. Let's see, let's make sure that our inspector isn't overriding our value here. Yeah, so the mass is being set to 1 still. So let's set it to 1,000. So it should be really slow. And you can see I'm kind of going the wrong way now. At least I'm moving correctly. And that's because the orientation of the sprite does not match up with the orientation here. So you can see we are orienting. Again, we talked about quaternions a lot in that quaternions are sort of relative to something. Here we're relative to 1, but our sprite is pointing up. So how do we fix that? Well, we need to rotate our sprite by negative 90 degrees. And now, well, that should have worked. Great. Well, why did it not update? I don't know. Well, what we can do is let's go and edit this in the sprite editor, and we can maybe rotate it here. Let's do center. This is something a lot of you guys had issues with in the assignment as well. So let's go into the prefab and make sure that this is done correctly. Great. So why is this not updating this guy? Well, whatever. So let's just delete it. Let's add a script. Our script is still here. Just have to apply it to it. Here we go. There. So you do have to kind of mind this in that you want to make sure that you're applying stuff to your prefab, not to the object in your project. Otherwise, sometimes you'll get different results. And so it's a little bit annoying with Unity sometimes to make sure that you're using the right thing, but it's important to do so. So now the orientation of the sprite lines up with the orientation, well, no, apparently. What is going on? Oh, of course. This will automatically reset everything for us. So this will not actually work still. So what we do need to do is there's two options. We either start off with like a 90-degree thing, or we can just kind of cheat and set our orientation to be 1, so pointing up, and that's going to correct our direction. So now if I point up, left is the right way, and now you can see now when I apply a force in a particular direction, so if I want to go the opposite direction, I just shoot a force in the opposite direction of which I'm traveling. Right, so if I'm going this way, I kind of have to aim opposite of this direction, and I can sort of slowly come to a stop. Cool. All right, looks and feels good. I think we're on the right track. So now you can see, by the way, if I go into my sprite, and I go into this vehicle script and I change the mass to 100, notice before it was quite slow, but now it's way faster. I haven't done the warping yet, which I'll do in a minute. Right, so again, we're summing the acceleration. The acceleration is sort of like a aggregate, like accumulation of all these different forces. So if you imagine in the update loop of the vehicle, we're going to add a bunch of forces, and then we're going to have a resulting acceleration from all of those different forces. So for example, let's talk about, well, let's do a couple of things. First of all, I'm going to mess around a bit with my script. So there's a couple of things I want to do. First of all, I want to, let's call it constrain position. Okay. And then void constrain position. Great. So the first thing we're going to do is we're going to create a kind of warp. So let's do the following. If at this point we have our point position, right? If point position is greater than the how do we do this again? Okay, let's actually make it a bit easier. Float world screen height is going to be equal to the camera main orthographic size 2.0. So what I'm doing is I'm taking the orthographic size by 2. This is usually like going to be just the value of 2. And screen width is going to be world screen height divided by the aspect ratio. Oh, does it have aspect? There we go. And great. And now what I want to do is if my my point position dot x is greater than world screen width, then point position is going to be equal to 0. I might be doing this completely wrong. I always screw this up as well. A lot of you guys had issues with this, and I'm kind of doing this also to help work this out. I'm not going to do the double one I talked about. Okay, if less than, then we want it to be equal to this. If it's greater than, we want it to be equal to that. If it's lesser than, 0. If it's less than 0. Okay, so this will hopefully do a reasonable wrap. Let's see what happens. Compile. compiler error. Constrained position does not exist and blah, blah, blah. Okay. Because I don't know how to spell. Okay, great. With a bit of luck, it'll be wrong. Obviously, it's wrong. If position X is greater than the camera, let's do this. Right, divided by 2. Then we want it to be negative. Then we want it to be positive. I want it to be negative. And it's less than that, and we want it to be positive. Let's see if I did this right now. I'll explain it if I did. Yay, great. Okay, so I'm not doing the most complicated thing here. What I am doing is, so what's going on is the way that the 2D system in Unity works is you have this orthographic projection, which we haven't talked too much about, but it's effectively like taking the world and squishing it down without any perspective. That size, you can actually see it here. This is the camera, right? And the camera, you can actually see projection orthographic size 5. If I change this, that's actually the value I want. I want to be working against that value. I don't want to be working against the screen size, because the units of the screen and the units of the camera are two different things. And what am I doing here? The only thing I'm doing is the orthographic size is this sort of sizing, but then you do have to figure out, to get the height and the width out of that, you need to apply to it the aspect ratio of your screen. So you'll notice if I change this, you'll notice that the orthographic size in my view is changing as well. And the way that you do that is an aspect ratio, right? So the aspect ratio is going to be the width over the height. And that's really what I'm doing here. I know it's kind of like a wacky looking way to do it, but this math would work exactly the same, right? Where the aspect ratio is simply the width divided by the height, and now you're taking the orthographic size times 2 and getting that. And the reason that I'm doing this greater than the world screen width divided by 2, the orthographic size goes from -1 to 1, and -1 to 1. So the orthographic size gives you half the width, right? And to get the actual scaled up versions, you have to multiply it by 2 to get by the width and the height of the actual screen. And so that's the reason I have to divide it by 2, because the x and the y is actually going to be, you know, from the negative value to a positive value of half the screen width. If you want to, you can adjust all this stuff, but it's a lot easier to work in the coordinate space of the camera, which is kind of what I'm doing here. Great. So here's another thing I want to do that might be kind of funky. So this is the, this is the right side of the screen. This is the left. This is going to be the top. I believe it's the top, and this is the bottom. And I actually I don't want to wrap the bottom. If this goes to the bottom, what I want to do is actually, I want to do something else. For now, I'm going to set y to be equal to 0, or to be equal to this. So I'm not going to let it go below the bottom. Oops, I keep on hitting play. Cool. So what this is going to do is it's going to halt my ship, as you can see. Great, something's wrong with my orthographic projection now. Maybe I did the math wrong somewhere here. Great, okay. So apparently the math that I was doing was wrong. I'm not entirely sure why. That because it's an int, of course, friends. Always the int errors. Okay, this is something everybody's gonna hit at some point. Casting is a thing, so be very careful. These values are usually less than 1, or they're fractional. Make sure that you do this correctly. I keep on hitting compile in Visual Studio. Okay, now we'll still wrap in this direction. However, if I go, I should, oh, right, so if I'm less than this, I want to just get stuck there. So again, this is the right, the left, the top, and the bottom. And now, if I go down, hopefully I'll just get stuck there. So this is sort of like getting stuck at the edge. Great. In fact, I might do that with all of them. So if you take the wrap, and there's a reason why I'm doing this, by the way, and you'll see in a minute. And now I'm just going to get stuck at these edges. Another thing you might want to do is you'll notice I'll get stuck at these edges, but my acceleration, I have to kind of overcome it before. So another thing I might want to do here, and this is so that I kind of stop. And this is not very physically accurate because maybe you want it to bounce, right? So actually we could do that. How about we do the following? We go, if we hit the edge, right? What we do is we do v-acceleration.x is going to be equal to -1 times v-acceleration dot x. Actually, constrained position is going to be done after, so that we actually want the velocity. And we actually don't want -1, we want it to lose some velocity. And for the y, we do the same thing with y. Also, I'm going to, this is definitely an else if. Can't hit both. Okay, so let's see what happens. So this is a very fun, simple thing. So now if I go here, it'll bounce me. It's almost like I hit the wall. But notice that I'm going to bounce slightly less each time. In fact, I can kind of play this game and see if I can bounce myself around the room. Cool. Fun. I'm going to get rid of the top, actually, and you'll see why in just a minute. Cool. All right. So now let's go back to our stuff here. Let's talk a little bit about friction. Now, friction is going to point in the opposite direction of our velocity. Friction doesn't always have to point in the opposite direction of our velocity. Friction can point in the opposite direction of many things. For example, we can be, you know, on a rough patch of grass, and So it's usually pretty relative to your velocity. You may be moving, you're running across the grass, like you have an object that's rolling across the grass, and so its effective velocity is pointing in the direction of the grass. But the grass is an irregular force, and it's bouncing you up and down like all over the place. And so it's kind of pointing in arbitrary directions. And generally speaking, friction will average out to against your velocity, but that's not always the case, but it's very, very close and approximate to the case. So, yeah, ultimately, yeah, we can get pretty good approximations in a game by assuming that it's pointing that direction. So to calculate friction, we can create this function, apply friction. It can be just a force, like we were talking about before, but let's kind of simplify this function. And let's do this. Void apply friction float coefficient, right? And what we need a friction vector. We need to normalize that because it's just the opposite of the velocity that we're moving in. And then we multiply the friction by the friction coefficient, and then we add it to our acceleration. So let's do that. Vector 3v friction is equal to just rv velocity times -1. And then v friction, in fact, we can just do this here, normalized. And then don't actually have to do all of that. And then just like we did before, we do v acceleration plus equals to v friction. Now you'll notice that there's no mass here, and that's because friction in this case is not related to mass. That's not always the case, but it's fine. Now, this is where we apply forces. You can imagine if you had a list of these forces, you could just put this into an array and loop through them, but for the time being, let's just do it this way. You have to make sure that you do all of these forces before you apply your acceleration to your velocity and your velocity to your position. Otherwise, you won't get affected correctly. And let's do a coefficient of 0.01, or let's do 0.5, just so we can see the effect more clearly. Great. So now, when we move, something went wrong. Let's try this again. So now when we move, great. Something really went wrong. Let's make sure that I didn't do anything dumb. So okay. Maybe this is too much. Not entirely sure why that happened. Clearly, something is very wrong. Okay. None. I think this is not actually the right way to do this. We need to take into consideration our mass in this friction calculation. Otherwise, we're going to have a very outsized friction force that is not technically correct. And so one way to do this is, instead of directly do this, you pass the friction force in through the apply force function. So I'm not sure this is something anybody else caught in other lecture or sections, but you can kind of see now it'll properly function. Great. So remember, we now have a little demo where we can sort of drive at the walls and bounce off of them, drive at the ground and bounce off of it. We slow down just a little bit. Let's slow down a little bit less. Let's slow down 10%. Great, so now we have friction. And now let's do, finally, gravity. And to apply gravity, it's similar. We can create a new function that simply adds the force of gravity in the direction of gravity, and gravity always points down. So in the way that before our velocity, our friction force was pointing the opposite direction of our velocity, our gravity force is going to point down. So let's go back here and create a new function called void apply gravity. Now, the fact is, gravity is not like friction or force. It is not mass dependent. It's not direction dependent. It's always pointing down at negative 9.8 meters per second squared. So we don't actually have to do too much, except create this new vector, and it's pointing down, right? And then we multiply, so we're 9.8 times it. You could also do add, and then it's negative 9.8. That also works. Great. And then finally we apply gravity. So now you'll notice I can't actually get off the ground because I'm getting pulled down. I can move to the left. No, I can't. Can't really do anything. It's because our gravity is extremely strong, right? The force being applied to us is 1,000 kilograms times the acceleration of 9.8, which is pretty heavy. So now we have to get into real numbers. We have to start thinking about, well, first of all, what if we reduced our vehicle's weight to 10 kilograms? Okay. And then next, what else do we want to do? Well, this is 9.8 F per second. And that's not good. So this kind of gets actually into our delta time, into how we need to multiply this by some kind of delta. Actually, we have this delta time function here. And I know this is only being applied to gravity, but we'll get there to everything else. So let's first of all slow it down, because right now we're getting too much. Great. So at least now it's going a little bit slower. What else do we need to do? Great. Oh, and we also have to multiply it by, well, actually, what we can do here is do this correctly. So let's do this. Let's actually calculate the force that we want to apply. Vector 3v gravity is going to be negative 9.8 times our mass times a new vector 0, 1, 0. Actually, we don't need to do this. Here we could do just like that. Great. And now we apply the force v gravity. And you're like, well, wait a minute. Didn't we just do that? But what will happen is we apply this force, we add it to acceleration, we divide out the mass. So once we do this whole thing, it'll just be 9.8f. So we should get the same thing, and it'll just get stuck at the bottom. Great. No, another thing we need to do is now we need to really think about the delta time. So now we only need to apply it here to the acceleration because everything's going through here, and the delta time will apply our things, which everything is measured in seconds or over seconds squared, and this will apply this correctly. In fact, we need to do this to the square because time, the acceleration is measured in distance over time squared. Great. So that looks more physically correct. However, our acceleration, our force, is not working at all. Barely to the right. So what we need to do now is we need to increase our force in the direction when we're trying to fly. Now, one way to do that is just to multiply this force by 10. Oops. You can see it's still not enough to overcome gravity. And that's because I weigh this thrust is related to how heavy I am. And I weigh, in this case, I weigh 10 kilograms, and I'm being accelerated at 9.8 meters per second and down, right? So that's 980 kilograms, like a force, or 980 newtons down. And so to overcome gravity, I need to be applying 980 newtons up. So even 100 will not do. In fact, if I take my mass, another way to create this in a way that will actually do it, if I want to overcome gravity, I need to have my mass times a value over the acceleration due to gravity. And now I should be able to just barely hover above the ground if I hold W up. So I can't quite overcome gravity. So there's something wrong with our code here, because even here I should not be able to overcome, gravity like in this way. There's something clearly wrong. Okay, so what's going wrong here? So first of all, to debug these things, it can get kind of annoying to have other things in play. So first thing, let's get rid of gravity. Let's get rid of that. And now let's see what happens when I apply a force. That's good. Great. So this is working. Now when I apply gravity, I want to go in the opposite direction. In fact, I want to set this exactly to 9.8 f. So at this point, the acceleration, the force that I'm applying up, should be exactly opposite to the direction I'm being applied to down. So let's see here, and in this way, I should just be able to hover in that moment. yet. No. Right now, I'm seeing we have some kind of bug. Because I'm able to overcome gravity's acceleration, when in reality, our acceleration should be, well, this is interesting, right? So is this physically accurate or not? It's really hard to tell. Because technically, if my acceleration due to gravity is equal to the acceleration that I'm applying in the upward direction, the two negate themselves, and I should be able to maintain the same velocity. So in a way, this is correct. As you can kind of see, I'm able to overcome gravity when I have a velocity. It'll maintain that velocity, then I can get up to a certain height, let go, and then pick up again on that velocity. And then I get up to this height and I let go, I can again pick up on that velocity. But then when I get to a certain height, if I change the direction, I no longer can do that. So I guess technically that's correct. Is that what we want though? So one thing we can do is we can apply friction to kind of help make this more physical, right? Where now what will happen is if I'm trying to push up, oops, if I actually have a significant amount of friction, it will slow me down. Still doesn't feel right. First of all, I want to increase my thrust. My maximum thrust should be like 15, 25, so I can play with it a little bit more. Keep that at 15. You can kind of see you can play with this for a long time. And the key is when I bounce, it should be way less than 50%. That's like bouncing off of a trampoline. So what I want to do is I want to maybe bounce with very little reactive force. So now what will happen is I don't have much velocity I can take advantage of after the bounce. Right, so now I can kind of like try to hover. I can move around. So if you've ever played that game, Lunar Lander, this is how you would make that game. Another thing I don't love is I'm kind of in the ground. And so another thing I can do here is I can just apply kind of a faux thing, and also my position plus my what I need to do is I need to Okay. And then sprite. Great. And then okay, let's see. I'm trying to have it not go through the ground. All right. Great. So that little bit of code will just sort of get my sprite bounds, and that way, all right, that's not what it should have done either. Will eventually come down. Okay, that's not really what I meant. Lots of fun bugs. Hold on. I'm going to pause until I resolve all these silly little issues. Okay, so I fixed the issue, and I think that this is actually something you got a lot of you people, a lot of you guys hit in the last assignments. So extents and bounds and size and stuff, it gives you it in world space. Well, actually not in world space. Sorry, in the sort of the extents of the object, and not necessarily in the world space. And you actually have to transform it by your local transformation. So to do that for y, you actually have to do that for this, because I scaled the sprite down to 30%. I actually have to multiply the transformation by everything. Great. So now, ideally, I've got a pretty fun little game that will let me land, bounce me off things, which is pretty fun. Right, and now I can sort of do some fun things with this. Notice that it's not actually taken into consideration my transformation, my rotation. So if I'm here, it'll work, but it won't work. It won't do proper collisions when I'm, rotating about. To do that, I'm not going to do that. But to do that, I would add that transformation again here to calculate the correct orientation of my bounding box. And I think that for those of you who had issues with collision detection and the correct collision detection, doing that, this is most likely why. Right, so cool. Now we've got this little toy game that you can kind of float around, fly around, try to stay up in the air. When you hit the ground, you'll effectively land. Notice that you don't land and bounce into the correct orientation, you just land and lay flat. And that's something that you would need rotational momentum to do, but we're not going to talk too much about that at this point. So yeah, that's kind of it. And so just to kind of go back a little bit about how you would generalize this. So gravity is obviously also special, but you can generalize a lot of these things in a kind of like an inheritance structure if you'd like. Designing a special class that handles different kinds of forces, you can do this for friction, you can do this for gravity, you can do this for thrust, you can do it for other things as well. We already kind of talked about delta time, and that, you know, when you are using these calculations, it's good to do it against a time frame. If you don't use the time frame, you are using a time frame. You just don't realize it. That time frame is a second, and that second is being divided by your frame rate. And so that's what we were kind of running into when we're doing the demo right now, where I had these numbers that were really outsized in their impact on the demo, and that's because we're taking numbers and multiplying them over a second, but we're actually hitting a time step of about, you know, maybe say 60 frames per second, and so we're basically multiplying that force by 1 second divided by 16 milliseconds, which is by 60 effectively. So our forces were 60 times more powerful than we intended them to be. So multiplying explicitly by the delta time will let you then actually apply the force correctly to the amount of time that it occurred in with the acceleration. This is very important with gravity, as we saw when we were trying to build it ourselves. There's another couple of Unity APIs you should be aware of, like unscaled time. So unscaled time will not take into consideration the time step or the sort of resolution of Unity. Unity can run at different frame rates, at different time scales. For example, if you're paused, you can change the scale of the time in Unity. Also, if you prefer to run on a fixed time step, instead of using update, we would use fixed update. And the way you would do that actually is just go, we're going to do this, say, update is called once per frame. We're not going to do anything in here, and then we're going to go fixed update. And it should work approximately the same way. It's a little bit slower, but it's a bit more predictable. If you looked at the math, you would see that a lot of the behavior is a bit more correct. You'll notice that, for example, gravity is applied a lot less rapidly than previously. And that's because it's not running as fast as it can. Let's kind of really quickly take a look at the difference between fixed update and update. Here, boom, great. But if we were to go to just update, you'll notice that it's a little bit less predictable, but once we are running, it's a lot more predictable. You can't quite see it probably in the video, but it's a bit more stuttery as well. So when you're using fixed update, things are a lot more predictable because it's on a fixed time step. Right, like here we go. In fact, the further thing is go unscaled delta time. And now this is going to be much more predictable in that we can kind of trust the data. Although you can see in time, you can get the time scale, you can get a lot of this stuff. You can even have this thing called smooth delta time, which will give you a slightly more friendly number. So again, the time scale that you choose, the time step, does affect the play, and not to mention if you're doing a multiplayer game or something like that where multiple computers have to synchronize, it's something really important to note. So yeah, we already talked a little bit about this, but let's talk about it again. Right, if you're doing a frame-based movement and you're running at 30 frames per second, in 1 second this object will move at 1.5 units. Right, if you're running at, you know, doing this in time-based, the amount of time it takes to cover this distance would be half a second to travel 1.5 units if we're going at 3 full units in a second. So you can see how choosing which one to do will ultimately change the behavior, and so you do have to kind of take into consideration time scale. I really do recommend putting this in only one line of code, and that's actually why this architecture is a little bit is good, where all forces funnel through a specific apply force function versus manipulating the acceleration vector on their own. So here we go. This is kind of the final code. You can kind of see you apply all the forces. You then apply your acceleration to using your delta time. You can do that here. You can also, I guess you also have to do that. Actually, that's better. That's a better design. Agreed. So let's move that down here. Instead, we apply it directly to the to this, and notice that we don't. This is not in this slide, but you really should think about it this way. Delta time should be to the power of 2 for acceleration, and not to the power of 2 for velocity. And now everything's kind of slow as a result, because our velocity is super slow. So, I don't think you need to do that. Actually, you don't. Okay, I guess if you do it correctly, you don't need to have multiplied by velocity. If you do it just one time, rate of change per second for velocity is that, and this is fine. Yeah. So you don't want to do it in both. Yeah, sorry about that. Again, the acceleration is distance over seconds for velocity, but is distance over seconds squared for the position. So if you were applying velocity acceleration directly to position, you'd do it that way. Sorry, sorry for the confusion. I would keep it as this. Apply both to both. Yeah, and that's about it. Please read the following. These should be also in my courses for the next week. Please take notes on these. Again, like as you saw me kind of bumble through all this stuff, these things can be a bit tricky. There's very minute differences, and I think that it's quite helpful to really visualize things and understand these particular things mathematically as well. So that's it for this lecture. Next, we're going to talk a little bit about autonomous agents and how to start to apply behaviors to things that that start to move in reaction to other things, not necessarily based on physical forces.